hours and 1 minute. And this is going to take up time. No. Take out the class for about an hour out that time. And then I think we might finish up I just feel like it's decent to an extent.
Nice to meet you too. You came in the talk. There you go. This is what I talked about. So you're going to talk to the kids for a few minutes? Yeah, I'll let you do that. What we're going to do is let you do your thing for about 10 minutes. Okay? So you don't think you can distract me? Okay. So I'll just make a couple announcements up front and then we'll move on. Huh? Yeah.
And I wanted to ask him questions about the big center. I know, I wanted to, but it was so awkward. I was like the Asian quarter of the table. Simon Red was there. Oh!
All right, the attendance sheet is going around. So on the agenda for today, we got to finish up some course business. Okay, we've got a guest that I'm going to introduce in just a moment as well. But finishing up the course material, we're going to pick up where we left off on electrical systems. And yeah, I should have just about enough here to close out the lecture. Before I do that, I just want to point out final exam and review session, final exam reminder. Right, it is 1 week from today during the unscheduled block, which is 12:30, 2:30 p.m. and 109 Ullman. Different from the other exams, you can bring 3 crib sheets, not just 1. Right, and the idea behind that is you could bring the last 2 you already made if they served you well, and then you can make a 3rd one. Or you can say the ones that I had before were useless to me, and I'm throwing them away, and I'm making 3 new ones. Okay, but as long as they are handwritten, both sides handwritten crib sheets. Okay, so that's a difference, that's per the syllabus. And here's the review sessions. All right, starting this weekend on Sunday, Tyler's going to be doing one. Then we've got Ghazi Monday. That is during finals week. It's an unscheduled block. Okay, we did that on purpose, so nobody should have a final exam during that time. Okay, and then Wednesday, we added one. I hope I did the right thing. Angie scheduled this originally for 8 o'clock a.m. And I felt like, you know, it's more than 24 hours away from the exam, and it's 8 o'clock in the morning, and she did that because it's an unscheduled block at 8 a.m. But I said you guys are going to be either sleeping and or cramming for your other finals that are that day. Right? So I said, can we do it at 8 o'clock at night? And now I will let you know, the room we have for that last one only seats like 40. Okay, so your best bet is to get to review sessions, you know, as you go. And we've got the Sunday one, we got the Monday one, and you can see we've got that right in bigger rooms, RC 144 for the Monday one with Ghazi, right here. Okay, and then office hours, of course, all week long too. We'll be having people in the Success Center. Okay, so you should be in good shape to prep for the final. Let's see, what else? We need to do course evaluations for this class. And I'm going to leave during that, but we need to multitask because we got a time constraint here. I got to get through the rest of the material. And so we have a guest today. We have Jessica with us from the Brandenberry Career Development Center, which is our new initiative to really give you guys opportunities to get jobs, okay, and develop career paths. And so I'm going to give her the whole time that you guys are doing evaluations. I won't be here, right? So we're going to pass these out. And so can I get a volunteer? Ricky, I'm going to solicit you. Ricky is going to pass these out, and then he's going to collect them. You have to use pencil. It will not read it if you fill it out in pen. Okay, and it's fill in the oval kind of questions, but then it's also comments. Take the time to put comments that you think will be constructive about me and or the course, okay, and put that in. And so we'll do about 10 minutes. Ricky will collect, and then Ricky, you will bring them back up yourself to the dean's office.
All right.
Okay, when we're done. And 10
Thank
minutes,
you.
and I will return.
Great. Perfect. So again, my name is Jessica Melita, and I work in the Brandenberry Career Development Center. Has anyone heard of that before? That's okay if you haven't, because we don't really exist yet. So, I was basically hired on to help you all with internships. So that's good, because you all are going to need internships before you get a job. So what we do in our office right now, we're located in the Engineering 1010 Help Room. So hopefully you've all been there at least once getting help. So if you don't know where that is, it's Engineering, it's Josie 280H, and we're in that side little section, and we're in the cubicles in the back. Has anyone seen us back there? I'm like, who are those two ladies? Maybe, yeah. I know I've met with some people already. So I also work with Cheryl Kent. Has anyone seen emails from her? Probably. Good. So making the connection. So Cheryl sends out emails each week. They used to come on Fridays. We started sending them on Tuesdays because we figure you probably don't check your email that much on Friday. You're either in class or entertained by what's happening on the weekend. So you'll get things on Tuesdays, and basically you'll see internship opportunities and then later on full-time opportunities. So still look at those full-time ones, because when you're looking for full-time jobs, you might want to start to know what types of information you need to know or what you can talk about during your interviews. So sometimes those job descriptions are really helpful. So on our website, this is new, so right on the College of Engineering Computer Science website, if you go to this careers option, so it makes sense, we're at the Brandenberry Career Development Center, and as I said, we're in Engineering 1010 Help Room right now, but the conference room right next door, I know it might disappoint some people, right next door, we're actually going to be in there. We'll have kiosks where you can work on your resumes, LinkedIn profile. We're going to have an office for myself, an office for Cheryl, and in the front there, kind of where there's those two round tables that I've seen people studying at, there's actually going to be an interview room there. So that's kind of neat, because as we bring employers to campus and they say that they're interested in you all and your backgrounds, you'll actually be able to interview right here on campus for opportunities in Cincinnati, Dayton, Indiana, wherever they're kind of coming from. Because for them to come on campus and interview 5 of you in a day is more efficient than spending, $50 a person to kind of give them travel reimbursement or something. So that's something we're going to be doing there. We'll hopefully be in there in January. So also on our website right now that you can start to kind of know about is we gathered all the internship sites thus far for people that have done an internship through Career Services and through our office, even though again we didn't really exist until this semester. So you can start to see, hey, I know IBM, probably everyone knows IBM, but you can actually start to see some of these other employers' names that have hired your colleagues before and know about Wright State and know what your curriculum is. So sometimes it's really useful to start with those sites, because sometimes if you have a friend that's leaving and they say, oh yeah, we really liked Wright State's materials program, we want someone else from that program, sometimes that can kind of help you get it in. We also work with the base a lot, so if you're interested there. So that's kind of neat. So then you all would be students here, so that's easy. So also on our website, it gives you the different guidelines for engineering internships, and I've talked to the academic advisors, and I know that there's certain restrictions that you need to have certain things, but some people have worked before, other people have taken classes elsewhere. So even if you don't meet these, talk to your academic advisor, come talk to me. Sometimes we can figure it out, because depending on what experiences you've had, or if you need to keep clearance, things like that, we can still help you find an internship, because we want you to make sure that you're maintaining those things. So this kind of just has the general, so again, it's not requirements, more guidelines. So you have that on here. Then we'll kind of talk about a few things here. So the thing that we really want to talk about right now is next semester, you can sign up for Engineering 1900. So it's a 1-credit pass-fail course that you can enroll in to actually learn about internships and how to apply for them. In that course, you'll actually create a resume, you'll create a cover letter, we'll have you interview a faculty member to learn more about what types of things are their students doing in the industry. We'll have you interview an employer that's in the industry in one of the fields you're considering. And then I'm actually working right now to get employers from different companies. Reynolds & Reynolds, Tridec, Trudy, I'm trying to think of who else has said yes. The Design Knowledge Company, places like that. That they're actually, it's not just going to be myself and Cheryl presenting to you, it's going to be real live employers that could recruit you later on and giving you advice about this is what you should put on your resume, this is what you should talk about during an interview. So it's a really cool course. It's, again, 1 credit. Sometimes I know people are looking for like that 1 extra credit to be full-time. So basically, if you're kind of in between that 11 credit hour, kind of put you over there. And then later on, when you actually get an internship, these are the internship courses that we have that you can also get credit for. So this one, you can kind of see there that they may count towards your general or technical electives, and it's different for every person and it's different for every department. So depending on what you already use those electives for, that's when we say talk to your academic advisor, or it could just count towards your general credits towards graduation. So that's something that if you're doing a 10-hour week internship, that basically equates to 1 credit hour. So if you're working 40 hours a week, that equates to 4 credit hours. So you can come and talk to us, and then you basically fill out these forms, and then you fill out a form to say, this is what I want to experience during my internship, these are goals that I have. Your employer fills out their form that says, we're going to provide a nice, safe environment for the students. They're not going to be getting coffee, running errands. They're actually going to be learning things, using the systems, being a part of our work. So we work with those employers to make sure that you're all getting a good experience for the future. Then here we have a list of current opportunities. So this is actually pulled from, and here's our contact information. This is actually pulled, and I'll go back up here, from the Wright Search. So this is something that Career Services runs. So we work in collaboration with Career Services. So if you already have a contact there or you want help with your resume, you can come talk to me. You can talk to Career Services, anybody you want. And basically, Career Services, what they do is that they post job opportunities. So you would be a first-time user here. And then employers, the reason you want to post in here is you can apply for things that you see that you're interested in. But once you have your resume, employers can actually find you. So it's also a really good way that they can say, oh yeah, I'm looking for this type of student. I see that they have Python experience and that's what I'm really looking for. I'm going to reach out to them to do a first-round interview. And I can help with all that too, your resumes, interviewing prep, salary negotiation, all that kind of fun stuff. So that's kind of a quick overview of what we're doing in our office since we're new, so y'all can know about it. And I'll pass out this little box here so you guys can take my business cards. If you're gonna lose it, you don't have to take it. I'll just put some here in the back too. But you can always go to the website, find our information. You can stop in the EGR 1010 help room. If you need help, we're there. Monday through Friday, 8:30 to 5.
Hey
Any
guys,
questions?
pass the evaluations on to the side room and stuff.
Is that quick enough? EGR 1900.
Oh yeah, basically that one. I didn't write it. But that's funny. Well, else is if you have more let's say, there's one question. Are all the evaluated limit or
Almost, but no.
It's not like this matters, but I figured out this is one of those ones that has right
This has ready for 10 minutes? Oh, this course?
No, wrong. I said that this month of December has 13 best Friday. You know, I once did a calculation that every year there's at least 1 month that has a Friday the 13th.
That makes sense.
That's why it always pops up every year.
Yeah.
So
often.
that doesn't happen.
Yeah.
Maybe 1, 2, or 3 times a year.
Didn't we have one recently besides December? I thought we had one in like September.
I don't know. All I do know is that somebody came up with an idea for a horror film or something.
And then it just took hold.
Which horror film was it that you
I don't know. I don't think 13 is that unlucky.
Was it the guy with the hockey mask or something?
Oh, Jason, the Jason is with Halloween.
I heard those movies are terrible.
I've never seen it. I don't really watch. I don't really watch scary movies. They're not my style. I like more action movies. Batman.
It was poorly made, and
Yeah. If it's something that like entertains you, like it's not cheesy.
a genre that's not my taste, but the movies are poorly made. Like,
Right, it's just all the worst things put together.
it's like, if you're watching a movie that has a genre that makes sense, well, just like, that was actually pretty good.
Yeah. I agree. Have you ever seen 500 Days of Summer? Yeah, it's good. It's, you know, kind of a more indie type film and independent, but it's a good one. I would recommend it. It's not, it doesn't end the way you would expect all movies to end.
I like watching a guy who analyzes like emotions back. He wants to talk about the whole dance, but he recently put together a top 5 list of characters that fall into the category of best movies.
Yeah.
Number 2 spot went to
Oh.
yeah, that's really just how.
No big deal.
Fair, but it's how can I find stupid where someone actually works?
Yeah.
It was Bella Swan. That's why I liked it.
That's pretty bad.
He mentions how mean-spirited on sharing themselves. I know that when you that actually was interesting. If it was intentional, but it's not.
Yeah, it's just like that. Cool. Thanks. Good luck on finals. I'll see you all at some point soon.
This stuff is so fun. Because this is audio. Well, let's see if I can get a look at it. Not only does he wear my name, oh no. Yeah.
Soccer fan, I know way
better.
I just pat myself on the back.
I'm not saying that he's on my school board. Whoa, or my high school board. But he kind of did. I'm saying they make no sense schools to me per se. But I had to write one card before I even came. No big deal. Yeah. It's a really great reference. This is intense. Holy shit, this is walking out. What's up? I think it's the shit's head. See how, yeah. It's to see how good soon there will be only one. Yeah. They're dropping off like flies. There's a lot of apps.
Mission accomplished. We get it. You guys just want to study hall.
Okay, here. Play 1 plus 4, and then you do a ball. And then that red signature. What? Yeah. I almost said this before. Hey, did you mess with the Yeah. 100.
If I could hear about this in one
Yeah, you're not allowed to have one now. That's respect. Turbo, because I went to my high school. What? That makes no sense.
Holy shift. That's what it says. I'm just reading it. It's with an F. Shift. Okay. All right, so we've got precisely 1 hour to finish up differential equations and electric circuits. Should be just about right. Okay, and we were midway through, maybe a little more than midway through the low pass filter. Okay, so last time, low pass filter. Okay, and so what the low pass filter is, okay, is it's essentially an RC circuit, okay, where you got a voltage source, right, and a capacitor and a resistor. Okay, and what we're doing here is measuring the output across the capacitor, which is V of t. That's my unknown, okay, plus to minus. And over here, we've got a voltage source, Vs of t. Okay, and we actually said what that was. That was going to be sinusoidal. It was E sine omega t. Okay, so we had a sinusoidal voltage source. Okay, and so it turned out that the governing equation was RC V dot, okay, plus V as a function of time is equal to the voltage source, right? In this case, E sine omega t. And if we have a condition where the capacitor is initially discharged, okay, capacitor here, resistor there, okay, then we have no initial voltage across it, so the initial condition is V of 0 equals 0. Okay, so this was the equation that we set out to solve last period. Okay, and I think to summarize where we were, we got through the transient solution. Okay, and I think the result that we got for that was an exponential. It was V transient of t is equal to C1 e to the minus 1 over RC times time. Okay, so the time constant then, multiples of R times C. Okay, and then we went through quite a bit of effort, I think, to get this steady state solution. Okay, and the steady state solution, okay, looked like the following. Okay, we wrote it as a sinusoid with a phase shift, right? And so it was this guy, V steady state, okay, is equal to E divided by root 1 plus RC omega squared. Okay, that's all underneath the square root, times the sine of omega t plus phi. Okay, and the way we define that phi, right, is phi here was equal to essentially a tan 2, right, a tan 2 of RC omega, all right, minus RC omega. Okay, and so when that's a negative value for phi, then that would be a negative angle. Okay, so that's the same as minus tan minus 1 of RC omega. Okay, and so also to kind of recap, you know, how we got that, essentially the phi we were looking at, right, when we combine this is the angle phi, right, and what we had was, you know, tan minus 1 of b divided by a. So I think the b here, this is minus RC omega, and the a over here was 1, right? And then we had the square root of a squared plus b squared, and this guy is going to be then 1 plus RC omega squared. Okay, so that's the triangle that defined how we came up with the phi, right, from the addition of sinusoids. And I believe that's where we left off last time. We just got to the point of the steady state. Is that correct? Okay, any questions on this and where we left off? Okay, I noted last time that we did a whole bunch of algebra and trig to get here, right? Most of the solution of these things is manipulating trig. Okay, and again, this triangle is just the addition of sinusoids piece. Okay, all right, so great. So I got the steady state, I got the transient. Step number 3 is what? I need the total solution. Okay, and so what do? Right, total solution means add them up. Right, and so what I need is a V of t, which is the sum, V transient of t, plus V steady state of t. And so apparently, right, it's going to be an exponential plus a sinusoid. So V of t total looks like C1 e to the minus 1 divided by RC times time, plus the steady state solution, E divided by root 1 plus RC omega squared, all right, times the sine omega t plus phi. So there it is. What is still unknown at this point in the total solution? C1. How am I going to find a C1? What was that? Initial conditions, right? So always when I get to the total solution, I'll be back to the unknown constants that I always have with the transient solution. Okay, and so I got to apply an initial condition. Okay, so it's a first order problem. I got one initial condition, right, and that one is V of 0 equals 0, the statement that the capacitor is initially discharged, right? So how are we going to do that? I take V and evaluate it at 0, all right, and I just set it equal to 0. So I'll get C1 e to the 0, right, when I put in the 0 for time, plus this guy, e divided by the square root, 1 plus RC omega squared, times what? When I put a 0 for time, I'll still have this, sine of phi, right? So again, putting a 0 for the t, so this sum just becomes phi, so it's the sine of phi. Okay, and that's V of 0. This whole thing is supposed to be equal to 0. All right. So what is e to the 0? 1. So this is just C1 plus, I got this guy, e divided by root 1 plus RC omega squared. What about the sine of phi? What the heck's the sine of phi? I mean, we got phi defined over here, right? Phi is a tan 2. It's a tan minus 1 of RC omega. Can I get the sine of phi? Sure. What do I look at? Got the triangle right here, right? So the sine of phi, all right, I can see by looking at it that the sine of phi is what? Opposite divided by hypotenuse, right? So minus RC omega divided by the square root 1 plus RC omega squared. So I know the sine of phi, and so that makes life a little easier. I can now plug the sine of phi right here. Okay, and so we'll just go ahead and plug that in, what we just wrote. Minus RC omega divided by the sum, or the square root, 1 plus RC omega squared. So, again, looks like more need for some algebra here. What am I trying to solve for at this point? C1. All right, what about the C? Do I know C? What's C? The capacitance. Okay, again, just constantly when you do problems with parameters, keep your mind set about what is unknown, what's a parameter, right? What's a variable. Yeah, everything is known here except for C1. So can I simplify this algebra at all? Denominator is the same, so when I multiply the square root of something times the square root of the same something, I get the something, right? So this actually gets a little bit nicer, and this is negative, right? So when it moves to the other side, I can actually see right away that C1 will be a positive number, and it's just going to be, yeah, RC omega, not W, RC omega times E, right, divided by 1 plus RC omega squared. That's C1. Questions on that? So finally, then is, what's the answer? This is among the messiest answers that we've boxed the whole year. Okay, that's one of the reasons why this is the last topic. Okay, but yeah, I do have the answer all the way down to one final form, right? I got C1, which is this guy. So it's RC omega E divided by 1 plus RC omega squared. It's that whole coefficient, right, multiplied by e to the minus 1 over RC times time. That's the first term. Second term is just the steady state solution here, right? So it's plus, again, e divided by root 1 plus RC omega squared times the sine omega t plus phi. Put a box around it. By the way, what's E? The capital E.
Oh, the capital E, of course.
R is the resistor. C is the capacitor. Right? Omega is the forcing frequency, right, of my input. What's E?
The amplitude of the source.
the amplitude of the source input here. Okay, and it's important to think about that because at this point now I got an answer, and you might still be looking at that going, how do all those letters help me understand this physics? Okay, and it's actually pretty straightforward. This thing is called a what? Low pass filter. Okay, and so the question is, what do you do with a filter? Yeah, you filter stuff out, right? And so what am I filtering out is the question. All right, they use filters all the time in electronics in order to process signals. All right, so again, in audio, for example, if I'm designing, a stereo system and I need a bunch of bass in my woofers, all right, do I want to hear some like high-pitched buzzing or something coming out of my woofer? Yeah. Probably not. All right, and what if my woofer gets excited by something that would cause high-pitched buzzing? All right.
What's a woofer?
Woofer, yeah, sorry. Speakers, right? So the woofer is the big part that gives you the bass, and the tweeter is the little part, the small one that gives you the treble. You guys with me?
Thanks for clearing that up. I had no idea what you're talking about.
Okay, good. So that's a woofer, and you can buy subwoofers, right, to give you really big bass in your car. Okay, and so.
I wouldn't want that.
So if I have a woofer, right, and I want to have big bass, then what I don't want is I don't want high-pitched buzzing and noise and such, right? And so what I would like to be able to do is, if I excite it with a signal that would be a high pitch, I'd like to filter it out, right? And I'd like to have, something coming out the other end which is not high pitch. By the way, how does pitch relate to frequency? High frequency is high pitch, right? Low frequency is low pitch. This is a low pass filter. Can I pass through low frequencies and filter out the high ones? Right? That's the point. Well, so let's take a look at this and see what happens. First of all, what's the solution look like in the steady state? This is kind of a leading question. What's that? It looks like the steady state solution, right? In the steady state, t approaches infinity, right? Which means this messy part that we did with the initial condition and everything else, right, doesn't actually affect the steady response. This is what happens right away when I first put a signal through, but over time this goes away because it's e to the negative right here. Okay, so it goes away like a decaying exponential, and what I end up with is a sinusoidal, right? So what that means, okay, is that I get v of t approaching v steady state of t, right? Or v of t approaches this guy, right? It's e divided by the square root 1 plus rc omega squared, okay, times the sine omega t plus phi. Okay? So, how do I know whether or not I'm filtering anything out? If my input over here is my excitation, okay, so this is my noise that I'm trying to filter out. This is the answer that comes out of the other end, right? If this excitation, right, is a high frequency, you'd like whatever comes out the other end to be relatively minimal, right? That means you filtered it out. On the other hand, if this is maybe a low frequency, the omega, then I'd like to see something coming out the other end. Okay, so the easiest way to look at that is maybe just compare the amplitudes. All right, if I look at the amplitudes of the input and the output, okay, so let's consider this guy. Let's consider, we'll just do the absolute value, right, or the amplitude of this guy, all right, of the output voltage V of t, all right, divided by the source, Vs of t. Okay, just the amplitude is what that means. Okay, because the frequency is the same, right? Okay, I've got sine omega t plus phi, it's got a phase shift. This is sine omega t. So it's just the magnitude of the signal. Okay, then what I'm going to get here for V of t is the answer it's this numerator over here, right? E divided by root 1 plus RC omega squared. And the amplitude of the source is just E. So that's the ratio, essentially, this is output divided by input, right? And in fact, I'll write it here, output, input. Okay, so the ratio of the output to the input is that. Can I simplify that algebra? The e's cancel out, so it's really just one fraction here. It is 1 over the square root 1 plus RC omega squared, okay? That is the ratio of the output to the input. So what's the conclusion? Okay, if I've got high frequency noise, right, then omega is what kind of number? Small? Yeah, so for high frequency, I'll write this down, high frequency noise, which is what I'd like to filter out, okay, essentially omega approaches infinity. It's a big number, right? High frequency noise. Okay, and in that case, what happens to this ratio? The output divided by the input, right? That ratio is going to approach 0. All right, here it is. The omega's in the denominator. Bigger the omega, this thing approaches 0. Okay? So the point is, it's filtered out. Right? On the other hand, if I'm running a woofer over here to generate the bass, I don't want the low frequency filtered out. All right? So if I have low frequency input, right, then what does that mean? Omega would approach 0 in that case. Okay? And if omega approaches 0, what happens? The ratio of the output divided by the input approaches what? Yeah, if the omega approaches 0, this is going to be 1 divided by the square root of 1, which is 1. Okay? In other words, if it's a low frequency excitation, whatever comes in goes right out the other end. Passes right through. Okay? So this is a low pass filter. Right? So the point is, low frequency passes right through. Okay? And that's why we call it a low pass filter. Okay? And so the point is, I can line up circuits with different combinations of resistors, capacitors, inductors, do other things to circuits, right? And I can get the circuit to perform functions for me, right? That's what electrical engineers do. In this case, in an audio application, a simple RC circuit can be used to filter out noise, right? And I can tweak what kind of noise I filter out because I got parameters in here, right? So if I want this to approach 0 faster, right, then I would use smaller values for R and C. If I want it to, other way around, I could change the R and C. It's the product of the two that matter. Okay, and when I do that, that will also change how fast things move, right, between transient and steady state response. Questions? Low pass filter. Algebraically, I would say that's as messy, right, as problems get that we do by hand. In a circuit's differential equation, okay? But if you persevere through the algebra, you can get some pretty useful stuff out the other end. All right, last example of the term. Second order LC circuit. Okay, and what I'm going to do for this one, because I want to make sure I don't have to rush through the punchline at the end here, I'm going to back off of kind of the derivation. Let me just set the problem up, and we'll give you the governing equation. So if I have a voltage source here, and I apply it to an inductor, right, and also a capacitor. So Here's the inductor, all right? Here's the capacitor. This one's L, this one's C, okay? And this is the source, Vs of t. Okay, then if I want to measure the output over here across the capacitor, okay, and call that the unknown, this is plus or minus V of t here. So same idea, I'll have an input voltage here and an output voltage across the capacitor. Okay, and so it turns out, right, that if you take a look at the KVL, I'll have a voltage rise here, right, and I'll have a voltage drop across the inductor. Anybody remember what the voltage is across an inductor? Relationship between voltage and current in an inductor is what? L di dt, right? So I'll have a voltage here, an L di dt, a derivative in it, but that same I is going through the capacitor here, right? And so that I in the L di dt is actually C times what? C dV dt, right? So I got L di dt, but I is C dV dt, so it's actually a second derivative, right? So I got this drop here, which is a second derivative, this drop here, right, which is the voltage across the capacitor, V of t, right, as defined, and then I've got the Vs of t. Okay, and so ultimately, the governing equation just becomes LC times the second derivative, V double dot, okay, plus V of t is equal to the voltage source, Vs of t. Okay, that's it. Okay, so let's suppose that I've got a sinusoidal voltage and that initially I'm starting at the simplest point. Okay, so the voltage is initially 0. Okay, so if I do that, right, we'll call this guy E. I'll use a cosine since we used a sine for the low pass filter. Okay, and so if this is initially discharged here, then we'll have V of 0 is equal to 0. Okay, and if things are initially off, that means that the current going through here is also initially 0. What's the current? How's that related to the voltage across a capacitor? Yeah, so I, right, is equal to C dV dt. I of 0 equals C dV dt of 0. That's also 0. Right, so this second one means the V dot of 0 is 0. Right? No current means no derivative of voltage. So I've got two conditions here, ultimately. Okay, one is V of 0 is 0. Second one is V dot of 0 is 0. Okay, and so finally, to cap this off, let's replace the voltage with the actual source, E cosine omega t. All right, and let's put the initial conditions on. V of 0 equals 0. V dot of 0 equals 0. Okay, and now we've got a complete second order differential equation, okay, for the voltage V of t, okay, with two initial conditions. All right, so we've reached all the way to the last, half hour of the semester, okay, and so we want to try and crank this thing out, right, just like we would if it was time for the final exam, okay? Least amount of writing as we can do, efficient problem solving, right, but we got to crank through all the steps, okay, because when you have the final exam, you're going to have to solve a first order, you're going to have to solve a second order, you're going to have to show all the steps and show all your work. Step number 1 is what? Transient solution. And in order to do that, I do what? Right-hand side is equal to 0, okay? And so let's write that down. So I'll have LC, right, times V double dot, second derivative, plus V of t is equal to 0. Great. What's next? E to the st. So we'll say V transient of t is equal to E to the st in general. So we'll, yeah, go on. V dot is. Do I have a V dot in here? So I got V double dot, so I'm going to get another S, right? Okay, and so I'll have LC times V double dot, S squared e to the st, right? That's the double dot, plus the V e to the st is equal to 0. What can I always do at this point? Factor out e to the st. I get e to the st times what? LC s squared plus 1 equals 0. What about the e to the st? Never 0. Okay, so the conclusion is the other part has to be 0. LC s squared plus 1 equals 0. Yeah, so s squared is going to be equal to minus 1 divided by LC, right? So s is plus or minus j root 1 over LC. All right, because I take the square root of a minus number, I got the j. So the conclusion now is that the transient solution, V transient of t, V transient, right, is supposed to be C1 e to the S1t plus C2 e to the S2t, right, where what? S1 is the positive, S2 is the negative, right? So V transient of t is C1 e to the S1, that's j root 1 over LCt, plus C2 e to the S2, that's minus j root 1 over LCt. And if I know that these are e to the j thetas, then I also know that that's the same as what? Euler's formula. Euler's formula. And so when I realize that this is the answer, e to the j theta, do I even need to keep it that way anymore, or can I just write it as sines and cosines? Right? So this is what I would say. As soon as you realize this, you say V transient of t, I'm not going to use C1 and C2 anymore, because we know that C1 and C2 are probably what kind of numbers? Complex numbers. Okay, instead we're going to say, what if I use a C3? And a C3 would be times a cosine root 1 over LCt plus a C4 times a sine root 1 over LCt, like that. All right, so there you go. 5 points on a final exam. There. Transient solution. Okay, so the point here, guys, again, is on the final exam, right, in your homework, if there's any chance that you still need to finish it, okay, between now and tomorrow, you know, we don't need to see all the Euler formula part and the arguments about complex and real. Look, when you reach this point in a differential equation and you know your S values are imaginary, immediately you can just jump right to this, right? It means it's sines and cosines. Okay? That is standard practice. Even in a math class, they will let you do that. Okay? Go right from one to the next. Okay, so I got a tangent. What's the next step? Steady state solution. So how do I do a steady state solution for this guy? So step number 2, steady state. Yeah, I take a look at the right-hand side, right? And so it's the original equation. So I've got LC V double dot, right, plus V of t is equal to the right-hand side E times the cosine omega t. So the right-hand side here is my forcing function, right? This is my f of t. And so if my right-hand side is a cosine function, then what's my steady state solution going to look like? Yeah, V steady state is going to have to be some combination of sines and cosines, right? The most general result. So we'll write it as capital A sine omega t plus capital B cosine omega t. What don't I know in that equation? A and B. All right, so the goal here is what values of A and B should I put here in order to make this left side equal to that right side? And in order to find that out, I should do what? Plug it back in. So I'm going to need V double dot, right? So V double dot steady state. Can we do this in one step? Sure, right? Efficient solution. First derivative, go ahead. All right, so first derivative gives me cosine omega t, omega out front. Second derivative, back to the sign with a negative, another omega. So I'll get minus a omega squared sine omega t. You see that? Two derivatives in one step. Okay? Right here, b cosine omega t. So I get negative sine with an omega. Take the derivative again. Back to cosine, another omega, negative still sitting there. Negative b omega squared, back what I had, cosine omega t. Okay, if you're not comfortable doing this, don't. Do one derivative and then do it again, okay? But I'm trying to have truth in advertising. This is the way I would solve it. I would not write the extra line, okay? All right, so I got these two things. I now want to plug that in here. Okay, I'm going to go back over to this board where I got more room. So to plug that in, okay, we've got the left side, LC V double dot, right? So it's going to be LC times that entire V double dot. So it's both of them negative, minus A omega squared sine omega t, minus B omega squared cosine omega t. Okay, that is LC V double dot. Plus I've got V of t. Okay, and V of t is the first one, A sine omega t plus B cosine omega t. Okay, and when I add those two things up, I should get the other side, which is E times the cosine omega t. Okay. By the way, what's unknown in that equation? A and B, right? I got one term, two term, equals the third term. Sydney, do you need something?
One of your students in this class left their keys somewhere, so I was just returning them before they tried to get home. Robert Beatty? What kind of car do you have? Just make sure I'm getting the right person keys. Ford, I'm guessing?
Not the Chevy Mustang. Okay. All right, very good. Thank you, Sydney. Okay, so let's see. Look at the service you get when your prof is the dean. The staff comes right to the classroom and helps you out. Okay, so I'm trying to find A and B. I got how many equations there right now? Currently, I have one, but I need to get two. So I need to compare coefficients, sines, and cosine, right? Okay, so let's line up the signs first. Again, how would I normally do this myself in one step, okay, is I would take everything with a sign, right, and see if I can write in one line. So the sine omega t, I've got the A here, and I've got another A, and I got a LC omega squared, right? So can I write this as, this one's positive, so I'll write it as 1 minus LC omega squared. So this is the 1. This is the minus. Here's the LC omega squared. Here's the A. Okay. Times the sine omega t. Okay. And then I have a cosine term. So what goes with the cosine omega t? Gonna make some room. Yeah, so the cosine omega t here, I've got a b cosine, I got a b cosine here, but I've got, again, a minus LC omega squared, so it looks like the same number, right? 1 minus LC omega squared, but now it's b cosine omega t. All right, and that has to equal the other side, which is the e cosine omega t. All right, so I'm hearing some rumbling, so people need to be recapped, I think, on the algebra. So let me recap you again. Back to here. LC V double dot plus V is E cosine omega t. This is V, assuming the solution. We need to find A and B. This is two derivatives of V, right? Two derivatives of the sine gives me positive cosine with an omega, then a negative sign with another omega, and I'm back to this. This second derivative first gives me a negative sign with an omega, right? And then another derivative is a cosine with another omega. The negative's still there, so I'm here, right? So this is V double dot. Over here, all I've done is plug it in. This is LC. This is the V double dot we just wrote down. This is plus V of t. And this is equals the original right-hand side. All right, and then you realize that I got one equation with two unknowns. I'm going to have to do something about that. So you say the only way this can work with sines and cosines is group all the sines, group all the cosines, and then compare the left and right side of the equations. Grouping the sines here, I did efficient algebra in one line. You can go back and double check that it works. I need an A sine omega t times 1. That's this term. I need an A sine omega t times a negative LC omega squared. A sine omega t negative LC omega squared, that's this term. Right? And then I need the cosine terms. B cosine omega t times 1, that's this term. B cosine omega t times negative LC omega squared. Here's B cosine omega t. Here's negative. There's LC. There's omega squared. Okay? So this and this is the same as that, and it equals the E cosine omega t. So I encourage you to do this, right? When you do a line of algebra and it's complicated, back up and double check it. Make sure you've got it right before you move forward. Okay? Nothing more frustrating than like a page of algebra and finding the mistake way up there at the top. Okay. All right, good. So now I need to get two equations out of this, which would be how? All right, coefficients of each. So let's look at the sines first. On the left-hand side, 1 minus LC omega squared times A. On the right-hand side, what's the coefficient? E. Is it? So I'm looking at the sines, right? Yeah, so this is 0. Okay, so the conclusion is A is what? Yeah, A is 0, right? As long as there's one other possibility, this could be 0, right? When would this be 0? Yeah, if omega is not root 1 over LC, right? If omega is root 1 over LC, then this term could be 0 and A could be anything, right? So as long as this is not exactly that, which, by the way, that is the frequency of the tangent solution. It's starting to seem a little familiar. Okay, then as long as it's not exactly that, the A would be 0. Okay, great. So let's look at the cosines. The cosines, this coefficient, 1 minus LC omega squared times B, has to equal the other coefficient, which is E. And so clearly then I can solve for B. B is going to be E divided by 1 minus LC omega squared. Okay, so we're getting somewhere. A is 0. That's a result we like. Okay, it makes life shorter. So now we're to the point where V steady state. The A is 0. I've just got a B. So it's just the B, which is E divided by 1 minus LC omega squared. Right, and it's just the cosine omega t. All right, that's another 5 points on your final exam. It's a bit of effort, but it's worth 5 points. So I got a transient solution. I got a steady state solution. All right, what's next? Need a total solution. Add them together. So step number 3. Total solution, which is V of t is equal to the sum V transient of t plus V steady state of t. So I'm back to these two guys. So V of t, the tangent, I got C3 cosine root 1 over LC times time, plus I got C4 times the sine root 1 over LC times time, plus I got my steady state part, E divided by 1 minus LC omega squared times cosine omega t. There it is. What's unknown at this point? C3 and C4, still unknown. How am I going to find C3 and C4? Initial conditions, right? The last step. So I apply the initial conditions. Okay, and so let's first do V of 0, right? V of 0 gives me C3 times the cosine of 0 plus C4 times the sine of 0, right? Plus this guy, E divided by 1 minus LC omega squared, cosine of 0. And when I add that up, I should get 0. So what's the cosine of 0? So C3 times 1 plus, what's the sine of 0? 0. Cosine of 0 is still 1, so it's E divided by 1 minus LC omega squared, right, is equal to 0. And so can I get C3? C3 would be that constant, right? E divided by 1 minus LC omega squared. Negative. Forgot a negative. Right, it's on the other side. Negative. That's C3. Well, I could plug it back in, right? And so that's going to go here. Okay, and then what would still be unknown? All right, so how do I get C4? Do what? Take the derivative, apply the second initial condition, right? Now, I'm going to do this one the way that I would do it myself. All right, we're down to the last, less than 15 minutes of class. We got to get to the real-time action here. V dot of 0. How would I do this myself? Would I write an entire line of V dot? No. I'd do the dot in my head. I'd stick the 0 in and write the answer. Okay, so let's do that. What's the dot? The dot on a cosine is what? Negative sign. What about this 1 over LC? All right, so I'll have a C3. I'll have a negative. I'll have a root 1 over LC. And that derivative is a sine, but I got to evaluate it now at 0. So this is times the sine of 0, right? That's the first term. Plus the second term, I got C4. Take the derivative of the sine as what? Cosine. What about the 1 over LC? Root 1 over LC out front. Cosine, I'm evaluating at 0. So I get cosine of 0. The last term plus E, 1 minus LC omega squared. What's the derivative of cosine? Negative sine, right? Here's negative. Here's the sine. I'm evaluating at what? 0. And this all equals 0. Okay, you see how I did that? I took the derivative and I evaluated it all in one term. Okay, if you're not comfortable doing that, put a second line in between where you write the whole derivative out and then evaluate it. Okay, but this is the way I would do it myself. So, sine of 0 is what? So this is 0. Sine of 0 is what? This is 0. So the conclusion is what? C4 has to be 0, right? It's the only non-zero term. Cosine of 0 is 1, right? This is 1. So C4 is 0. So do I have two constants? I got C3, I got C4. I can go back to the final answer here. So what do I have for the answer now? Okay. I've got V of t is equal to C3, right? Minus E divided by 1 minus LC omega squared, right? That's C3 times the cosine root 1 over LC times time. C4 is what? 0. plus the steady state term, right, which is E divided by 1 minus LC omega squared cosine omega t. Can I simplify the algebra at all here? So I can factor out that coefficient, right? E divided by 1 minus LC omega squared. That goes out front, all right? And then I'm going to multiply this by what? Yeah, cosine omega t is positive. This one is negative, so it's cosine omega t minus cosine root 1 over LC time. Okay, that's it right there. This is the solution to the forced response, okay, of the LC circuit. Okay? Now, here's something I want you to note. This is the solution to this problem, which goes with this picture. Okay? If you remember, before Thanksgiving, we did another problem. We did this problem. M, right, and K, right? And we did this, F cosine omega t, right? And we had M y double dot plus K y of t is F cosine omega t. Over here, right, and what were the initial conditions? We had y of 0, y dot of 0 was 0, right? And over here, what do we got? LC v double dot plus v is E cosine with the same two initial conditions. We did this problem in full, right? Do you remember the answer? Right? Didn't we get, for an answer for y of t, right, didn't we get this guy? F divided by k minus m omega squared, right, times cosine omega t minus cosine root k over m t. Right, and can't you just then say that this is the case? Here's my spring mass. Here's my LC circuit. Right? In a spring mass, my unknown function is what? What's the unknown function I'm trying to find with the spring mass? What am I trying to solve for? Displacement, right? Y of t, right? That's this. Okay, what about in the LC circuit? I'm trying to solve for what? Yeah, I'm trying to solve for the v of t, right? And if you take a look at those two equations, you know, what are the parameters? In this problem, I got an m in front of the y double dot. What's in front of the double dot here? LC. So apparently if m is really LC, okay, and what else? I got a spring constant K, that's what's in front of the Y. What's in front of the voltage V over here? 1. Looks like the K would just have to be 1. Okay, and let's see. Forcing function. I got an F for an applied force on the right-hand side. What do I have here? I got E for a magnitude of a voltage. Okay. And so, you know, the point here is it's a completely different piece of physics, right? This is circuits class over here, okay? Completely different governing laws. Kirchhoff's voltage law, right? The voltage-current relationship across an inductor, a capacitor, all the rest. Over here, this is dynamics. Applied forces, sum of the forces equals MA. But when I'm done, I got a mathematical model for this physical system, which is identical to the mathematical model for this physical system if I just change the letters. All right, this is the other reason why we do problems with letters instead of numbers. All right, because now I can ask you this question. All right, because if you're a mechanical engineer and, you know, or just a first-year engineering student in general, and your prof put up all these MATLAB plots and tried to explain to you what happens if I force this thing at the natural frequency, right? Same thing that happens when you drive your beater car at 57 miles an hour, okay? Not his Mustang, right? What happens, right, if I force it at its natural frequency, it increases vibration without bound, right? It resonates. So then now the question is, you know, what happens if I take an LC circuit and I apply a signal to the LC circuit that approaches the transient response of the LC circuit, root 1 over LC? What's going to happen? What's that? Noise? Is that what you said? Yeah. Yeah, noise could be one. What would be worse? Short circuit, smoke, right? I mean, so I'm going to burn it up, okay? The voltage increases without bound, okay, is what happens, right? And so you can get insight into the physical system over here by understanding the math to a physical system over there. Okay, we use this stuff all the time in advanced engineering, like graduate level engineering. We think about a piece of physics is too hard to understand, but the math that goes along with it explains a piece of physics that's easy to understand, right? And so then you can understand the math. Okay, so the other moral of this story is there's only so much math, guys. Don't be afraid of it, right? There's only so much. A few key pieces of math can solve a boatload of problems, right? And that's what we did this term. Okay, so that's all we've got. And so final exam in a week, tons of review sessions in between. A couple minutes left if anybody wants to hang out to ask me questions. Otherwise, good luck in finals.
Khan Academy handles first order diffs in a totally different way.
Okay.
Is there a reason why we did it this way?
You know, which is the totally different way?
Well, maybe I'm thinking about different kind of equations.
Yeah, because the solution we have with the recipe is for linear equations with constant coefficients and a forcing function. Okay, they may give you some methods that are more general than that.
Integrals.
Well, so if you have equations that are called separable equations, then what you can do is, you know, essentially what you're doing is just recognizing that, you know, like suppose you have dy dt is equal to, you know, the cosine of t, you know, like that. You can separate this equation, right? And you can essentially put the differentials on both sides and integrate both sides. So there's equations where if you can group the differentials with the letters, they're called separable equations, and then you can do them that way. Okay, that approach doesn't work in general for linear equations with constant coefficients, so this is more general. But there's definitely first order equations that have an exponential result that are separable, so you can solve them that way. Okay?
Cool.
Yep.
Thank you.
You're a very good teacher.
Hey, thank you very much. Appreciate it.
Have a good week.
Okay, good luck.
My exam, back.
Exam number 2?
Yeah.
Was that it? What's your last name?
Quach, Q-U-A-C-H.
Q-U-A-C-H, Quach. Grading, oh, this is the one where you asked to look at number 3D? Mm-hmm. Is that right? Yeah, so it says new grade implemented in pilot. Let me see what they did. I had the grader look at it. 3D over here. So they gave you some points back there. So it looks like you got 3 points back. Okay, so there's the result. Yep. What's up?
This discussion was recorded today, right?
Uh-huh.
Okay, just want to make sure if.
So you can go back and watch the video? Yeah, the guys right now are taken down, or are they? They'll be in here at the end. So yeah, it'll be posted probably later tonight.
Okay.
Okay? Absolutely.
Can you know how many absences?
You know what? I am guilty of not being updated in Pilot yet.
Yeah.
So, but let me make that a priority and get that done in the next couple days so you can check, okay? So I've got all the attendance sheets for the last, I updated it last right before the drop date. So I had it updated before the drop date, and then after the drop date, I got a little lax. So I got all the attendance sheets, but I haven't input them in Pilot yet.
Okay.
Okay?
How many absences and
Your total allowed absences is 5.
so
Unexcused. If you have an excuse for an absence, then you don't get marked as unexcused.
so if I have 5 absences, I am the
If you're right at 5, then the consequence of that is you lose 5% of your final grade.
But
If you're,
I'm okay.
Yeah, you're okay. If you're at 6,
Yeah.
then you fail the class. So you
Okay.
got to be sure that we're there. So maybe even send me an email reminder if you don't see it updated in the next couple days, because important for you to understand what your situation is.
Thank
Okay?
you very much.
Yeah.
One last question.
Yeah.
The MATLAB final
Yeah.
grades will be posted.
Yeah, so I would imagine they will just input them in Pilot as soon as they have it sorted out.
Maybe by Monday.
I would guess so, yeah. The MATLAB grade part is a little more complicated for the TAs to sift through, but the turnaround's usually pretty good, so, yeah.
Thank you.
I just want to say thank you, Dr. Clean.
Absolutely. Okay. I'm glad you had fun. Good luck in finals week.
Thank you.
Yep.
I was just wondering how many classes you actually teach.
Well, anymore, not a lot. So I used to teach a ton when I was a regular professor, but honestly, as long as I'm the dean, probably this one class, one time a year is probably all I'm going to teach. That's just you should see my calendar, it's just completely filled all the time, so too busy with other